Hello, everyone. My name is Xiaoquan Li. I'm a PhD student studying automatic music transcription from the Center for Signal and Image Processing Group of the University of Strathclyde in Glasgow. And today, I'm going to present about how to recognize predominant music instrument by using Hilbert-Huang Transform and deep convolutional neural network. Before I begin, I'd like to really thank you to all the organizers of the conference in this hard time. This Black Swan event coronavirus outbreak truly impact this world and our life. Hope you guys are safe and healthy during this time. The coronavirus also changed our way of meeting and work, and it's also my first time to present in a live way. So let's start my presentation. I will separate it in three parts. Firstly, I will talk about its background and development of the predominant musical instrument recognition area in about 3 minutes. The predominant musical instruments are not like the monophonic music or single instrument. They perform together like a symphony or band. So this area is still a challenge. Secondly, I will show my research and completed work in about 10 minutes. In this part, we proposed a Hilbert-Huang Transform plus deep convolutional neural network method to recognize the instrument. And I will introduce its progress and evaluate its advantage and drawback in this part. Thirdly, I will discuss about its application scenarios in such as automatic music transcription and musical retrieval. So let's move on to the part 1, background. This area is still a challenge, and the current predominant music instrument recognition approaches have not been commercialized due mainly to lack of robust performance. The identification of a musical instrument depends primarily on its timbre. From the point of the view of physics, the timbre produced from an object is determined from its vibration state, which characterizes the object's waveform and harmonic properties. For a specific musical instrument, its spectrogram change is very complicated due to different playing techniques. The same type of the music instrument will have apparently changed in timbre. Therefore, identifying instruments in a piece of music is an interesting and challenging problem. In general, there are two kinds of musical data, monophonic and polyphonic data. In monophonic music, the instrument is played independently. Most of the work on instrument recognition is done under the assumption of independent performance, which simplifies the recognition task. In the case of separate recording, MIDI can store each instrument in a channel, making it easier for a single instrument to be detected. However, music is more often polyphonic than monophonic, such as in a symphony orchestra or recording live scenes. Recognition of a single instrument in a polyphonic music recognition is therefore much more difficult, and several attempts have been made for automatic recognition. Therefore, we can see that the predominant musical instrument recognition is still a challenge in music information retrieval and still needs to be improved. And what is our method to improve it? Let's move on to the next part. Part 2, completed work. The Hilbert-Huang Transform is employed to map one-dimensional audio data into two-dimensional matrix data, and then a deep convolutional neural network is developed to learn affluent and effective feature for predominant musical instrument recognition. In the experiment, 6,000 more audio pieces, including 11 musical instruments, are used to validate the efficacy of our proposed approach. The results are compared to four benchmarking methods and show significant improvements in terms of precision, recall, and F1 measures. In the proposed framework, in this figure, we used the Hilbert-Huang transform to generate the Hilbert spectrogram for each instrument in the polyphonic music piece. Then we built a deep convolutional neural network to take the Hilbert spectrogram as input and produce the classification label as the output. The Hilbert-Huang transform was proposed by Wang from NASA in 1998. This method is suitable for nonlinear and non-stationary signal analysis. At present, Hilbert-Huang transform technology has been applied in many fields, such as geophysics and biomedicine, and achieved excellent results. What is the progress of the Hilbert-Huang transform? It mainly includes two parts: empirical mode decomposition and Hilbert spectral analysis. We call it HSA, where the empirical mode decomposition is used to first decompose the given signal into several intrinsic model functions. We call it IMF. The Hilbert-Huang transform is then applied for each IMF to obtain corresponding Hilbert spectrogram. Finally, the Hilbert spectrogram of the original signal can be obtained by summing all the Hilbert spectrum of the IMF. And then, because we usually use short-time Fourier transform to make the signal from one-dimensional to two-dimensional. So what's the difference between the Hilbert-Huang transform and Fourier transform? The main difference is that the Hilbert-Huang transform can be thought of as a phase shift converter, and the traditional Fourier analysis use a series of sign basis functions to perform operation on signals. However, the resulting Fourier spectrogram is only the weighted mean of the frequencies over the certain period and cannot be accurately described by time frequency change. So let's move on to the next page. Our deep convolutional neural network was inspired by the VGG16 model, which contains 16 hidden layers, but ours is not VGG16. In this figure, we illustrate the architecture of the proposed deep convolutional neural network. There are 6 convolutional layers in the proposed model, where each convolutional layer is followed by a bench normalized layer, an activation layer, and a max pooling layer. The ReLU is selected as the activation function for each activation layer due to its polarity and ability to increase the learning speed. In the first convolutional layer, the street size is 2 times 2, which is changed to 1 times 1 from the convolutional layer. Both pooling size and street size of each max pooling layer are set to 2 times 2. In addition, the input for each convolutional layer is same padded in order to preserve the resolution. The number of filters for each convolution layers is twice that of the previous layer, increasing from 32 up to 1024 at the last layer. After the final max pooling layer, a dropout layer is added before and after the fully connected layer to avoid overfitting. At the end of the network, the softmax function is used to classify 11 types of instruments. After this model, we also use two adjusted hyperparameter to improve network performance. It's also a vital step in deep learning to get the optimal performance. We only vary the minibatch size from 50 to 300 in intervals of 50. From this table, the best testing accuracy can achieve 85% when the minibatch size is 250. As a result, the bench size in our experiments was set to 250, with minibatch size equaling 250. The classification accuracy of proposed model with varying dropout factor from 0 to 0.5 at a step of 0.05 is shown in this figure. It based on the result. The dropout rate is set as 0.25 is our work, where the performance is near the 85%. For the other parameters, Adam is used as an optimizer with a learning rate of 0.01. To future evaluate the effectiveness of the proposed predominant music information recognition framework, three convolutional approaches are used to benchmark in terms of precision, recall, and F1 measures. Three convolutional frameworks are based on audio content analysis. We call it ACA system, and then machine learning model. One is a random forest, another is SVM, and shallow neural network. For each music piece, ACA system is used to extract 19 features such as peak envelope, autocorrelation coefficients, MFCCs, and pitch chroma. Then this feature will concentrate into a feature vector. What's more, we compared it with a new HAS-IMF algorithm proposed in 2018 using the same dataset and computing environment. Results that, including the overall precision and recall and F1 measures, are presented in table. And in this figure, the F1 measures of each instrument is shown. As we can see that the proposed framework generated the best overall performance and outperformance conventional framework in classifying individual instruments. In this table, the ACA features are combined in the first three classifiers. Among them, random forest-based method seems the best, yet is significantly poorer than the HAS-IMF, due mainly to the integration of the Hilbert-Huang Transform spectrogram and CNN model. However, thanks to our improved CNN structure, the proposed model has significantly outperformed all these including HAS-IMF, where the precision, recall, and effort measures are improved by 50%, 50%, and 6% respectively. And what's the difference of ours and HAS-IMF? Actually, our model, the bench normalization and max pooling are followed by each convolutional layers, and the dropout layer are put before and after the fully connected layer. However, in HAS-IMF, a dropout layers is followed by every 2 convolutional layers, although the dropout layer can reduce the training time. Too many dropout layers may lead to the network not being fully trained. Furthermore, it doesn't include a bench normalization layer, which may lead to the data becoming unbalanced. Therefore, our proposed convolutional neural network model is better than the HAS-IMF and gives a better performance. Let's move on to the last part, part 3, application scenarios. A subtask of music information retrieval is predominant musical instrument recognition, which enable customers to search music by instruments, as well as making music transcription easier and more accurate. However, it's quite useful in some applications, such as assisting automatic music transcription detection through the instrument classification and instrument characterization. In automatic music transcription area, the predominant music instrument recognition can help it control variable, because the automatic music information is like an inverted performance. If the instrument is known, it will helpful. If we want to know which instrument they use, the musical instrument classification can be used in some scenario like symphony scenes and performance scenes. The predominant musical instrument recognition also can help us collect some features from each instrument and show they are different. It helps musicians analyze the music instrument, brand, quality, and other features. We can see that this area can help us a lot, and it will be used in commercial in the near future. Finally, thank you for your listening and best wishes for all of you. Thank you very much.